Okay, so let's take a look at your homework questions. First on the multiple choice sheet. Number 11, the field around a permanent magnet is caused by the motion of, should be electrons. The next set, base your answers to 12 to 15 on the following diagram, which represents a cross-section of an operating solenoid. A compass is located at point C, okay? So these are the coils in the solenoid. It's telling us this is the North Pole and this is the compass down here. Which diagram best represents the shape of the magnetic field around the solenoid? Remember we said today that the magnetic field around the solenoid is going to look like a magnetic field around a bar magnet. It cannot be this one then. It cannot be this one. It has to be one of these two. Okay, if this is the North Pole over here, it doesn't matter whether you consider it electron current or conventional current. We know that the field lines come out of this, come out of the north and go into the south. The only one that does this is choice 3. You should be able to tell choice 4 is wrong, even if you didn't remember the field lines came out of the north and into the south, because look, they're coming out on the top, going in on the bottom. Can't possibly be that. Number 13, which shows the direction of the compass needle at point C? So again, if this is the North Pole and this is the South Pole, the field lines are going to look like this. The compass needle always points towards, always points towards the south. So it should be going this way, which should be number 4. 14, if B is the North Pole of the solenoid, which they show us in the picture, which diagram best represents the direction of the electron flow? So finally they tell us which one to use. So I need my left hand, and the north has to be over here, right? So my thumb has to be on this side, which means my fingers are going to go in on the top and come out at the bottom. Into the page on the top, out of the page at the bottom. Into the page at the top, out of the page at the bottom. Has to be choice 4. You should never pick 1 and 2. They can't either both go in or both come out. If the current in the solenoid is doubled and the number of turns halved, the magnetic field strength should do what? Well, if the current is doubled, the magnetic field strength should double. But if the number of turns are halved, then the magnetic field strength should halve. And if you double and half at the same time, it should remain the same. Okay? Those ones done. So now on page 504, I asked you to do 9 to 12, and I promised you that they would be simple, like quick. So number 9 says a straight wire of 0.1 meter carrying a current of 2 amps is at right angle to a magnetic field. The force on the wire is 0.04 newtons. What is the strength of the field? F equals BIL sine theta. It tells us that the angle is right angle, so sine of 90 is 1. B is equal to F over IL. F was 0.04 newtons. I was 2 amps. And L was 0.1 of a meter. 4 divided by 2 is going to be 2. Move the decimal and get 0.2 Teslas. Number 10. A wire which is 0.5 meters long carries a current of 8 amps at right angles to a 0.4 Tesla magnetic field. What is the force? So BIL sine theta. B, it tells us, is 0.4 Teslas. I, it tells us, is 8 amps. That's about 3.2. And 0.5. So it should, meters, sine of 90. It should be 1.6 newtons. Number 11. A wire 75 centimeters long carries a current of 6 amps right angles to a uniform magnetic field. The magnitude of the force acting on the wire is 0.6 newtons. What is the strength of the field? So again, F equals BIL sine theta. So again, B equals F over IL. It tells us the F is 0.6 newtons. It tells us the I is 6 amps. And it tells us the L is 75 centimeters or 0.75 meters. So you get 1/10, that's 3/4, 4/3. Move the decimal, 0.13 repeating. Whoops, I said 0.13 repeating. My hand just didn't hear me. Teslas. Number 12. A copper wire that is 40 centimeters long carries a current, so L, 40 centimeters carries a current, sorry, that's equals, carries a current of 6 amps and weighs, so it's Fg, is 0.35 newtons. A certain magnetic field is strong enough to balance the force of gravity on the wire. What is the strength of the field? So if it's balancing the force of gravity on the wire, then the force of the magnetic field must be equal to Fg. So they gave us the weight, but they're really giving us the magnetic field strength. And so now it wants they're giving us the force of the magnetic field, and now it wants the magnetic field strength. So again, rearrange for B. It's equal to F over IL. So 0.35 newtons over 6 amps times 10 centimeters, or 0.1 of a meter. So 0.35 divided by 0.6, 3.5 divided by 6. It's not quite 1 point. I don't have a calculator to get the decimal. It's not going to be quite point. So, whoops, sorry. 0.35 divided by 0.6. 0.58? Did I screw up? I don't think so. I think the book did. I'm looking at the answer in the book and it's saying 0.15. So I'm going to have to balance the force of gravity. What is the strength of the magnetic field? I don't think I screwed up. 40 centimeters, that's what's wrong. There we go. It's like, why doesn't that match? Let's try that again. So now it's 0.35 divided by 0.24. Oh, and look at that, it's 1.458. 1.4583 Teslas. All right, flip over to the back. Number 3, a conventional current, so I'm on page 511 now. A conventional current is flowing in a wire as shown. Copy the wire segment and sketch the magnetic field. Okay, so it's showing us, this is the wire. The current is going this way. It's conventional current. So the field must be coming around like this with the arrowheads this way because it's conventional current. Number 4, current coming straight out of the page. Copy the figure and sketch, and your textbook always assumes conventional. Okay, so it's showing you the wire. It's coming out of the page. Copy the figure and sketch the magnetic field. So coming out of the page, the field lines are going to go around like this with the arrowhead going counterclockwise. Turn the page. Figure 2430 shows a view of an electromagnet with the current as shown. What is the direction of the magnetic field inside the loop? Okay, I could draw it, but not nearly as well, so let me just show the picture. Okay, so the current is going up around. It's assuming conventional current. So the current is flowing this way, so I need to take my hands and curl like this. And my thumb is going into the page. So it's going through the magnet, the electromagnet, and coming out the other end. So the other end must be the north, and this end must be the south. And so the question said, what is the direction of the magnetic field inside the loop? Into the page. What is the direction of the magnetic field outside the loop? Coming out of the page. Okay, number 6. A current carrying wire is placed between the poles of a magnet as shown. What is the direction of the force on the wire? So remember this hand rule was, and again, your textbook always assumes conventional. So your hand goes from north to south, and it says the current is going into the page, so the force must be going to the bottom of the page. And look, they were nice enough to put the arrow in there for you. All right, number 7. A room contains a strong uniform magnetic field. A loop of wire in the room has current flowing through it. You rotate the loop until there is no tendency for it to rotate as a result of the field. The direction of the magnetic field relative to the coil should be, the thing is sine theta, so it should be 0, should be parallel. A wire 0.5 meters long carrying a current of 8 amps is at